Hey guys, in this series of video, we will be exploring the components of an end-to-end machine learning pipeline. So we start from training and monitoring models to deploying them in production. We will cover every single step. So here I plan to give 6 videos for this series. The first 2 will be about model training, monitoring, inference, and ONNX packaging. The third to the 6th videos will be about the deployment of the model. In order to illustrate these steps, we will tackle the emotion recognition problem. So here, this series is done with my friend Nguyễn Quang Hạnh, and I hope that he has time to illustrate about model deployment. He is an expert in model deployment. So let's start with the first lesson, which is model training and monitoring. So here I have already written a blog post about the series. So I will include the link to this blog post in the description. Well, and here is the GitHub page for the code. So in the first lesson, we will be going through 3 main components. First, we will be preparing the data for the training. And second, we will write the VGG16 model that is used to handle this problem. And third, we will train the model. So for training here, in this case, I will be using Pytorch Lightning. The reason is because Pytorch Lightning is a library which comes with a lot of built-in features which could accelerate the trainings. So here is the script for the data. I guess it's better if I close the recording interface. So here we'll be writing a custom data class in order to load the data from a CSV file and then create data loaders. First, you need to begin by download the data file. So I will include the data file in the description of the video. After you download and put it in the root directory, here is the script for the preparation of the data. Basically, we will create a data class for data module that extend Lightning module. So this class will handle the dataset and make sure that the training and the validation data loaders are prepared for the training process. In the init method, we will basically set up the transformations that are going to be applied for the train and the validation data. So here we initialize the batch size, cut size device. Here I'm using a MacBook, so I keep the device to be MPS. For the train transformations, I use a composition of random crop, width size 44 by 44, random horizontal flip, and convert the data to tensors. For the transformation of the validation data, we have a composition of the so-called 10 crop. So the 10 crop here means we are going to crop the original image into 10 sub-image, each of size 44 by 44. So the cut size here is 44 by 44. Well, the purpose of this is so that when we do inference on a single image, we will be doing inference on the 10 sub-image, and we will be taking the average of the predictions. This trick will increase the accuracy by a little. Well, I should talk a bit about how the CSV file look like. So I guess this is not a good way, but just look here. So in the CSV file, there will be 3 columns. One is emotion, the second one is pixel, and the third one is usage. So emotion, here there are 7 emotions indicating just normal emotion like happy, angry, sad, neutral, and so on. The pixel here indicate the actual values of the human face. So by default, the pixel's size is 48 by 48. The usage here is training, validation, or test. So in the prepare data function here, we will be loading the dataset and put them into arrays, reshape into the shape 48 by 48. In the original CSV file, this file here, for the pixel columns, all the pixels here are flattened, so it is a vector of size 48 by 48. When we load this pixel, we need to resize it into size 48 by 48. Sorry. So here, let's continue here. So we initialize all the empty lists for the train data, train target, public test, which is used for validation, private test, which is used for testing. And we open the file and load it, and then read the content of the data, and then we will put the pixel into appropriate list based on whether it is training, validation, or test. So this part here is to load the data from the CSV file and put them into the arrays. The final step here is to reshape the size of the array to 48 by 48. So once we have loaded the data, we will be setting up the data so it will be initialized. So here for the function setup here, we will set up based on the state. When the state here is just a string which can be fit or test. When the state is fit, we will initialize, which means we will load the train data and the validation data, right? Using the get dataset function that is written down below. And when the state is test, we will be loading the testing data. So the get dataset function here simply load the data based on the given split. So what happens when we call the setup function is that it will automatically load the data for training if we are using the state to be fit, or for testing if we key in the state to be test. So whenever we call this function, it will automatically call the get dataset function. And here for the transform dataset function, it is used to apply the transform on the dataset. So the transform here can be the transform for the train data, or it can be the transform for the validation data. So we simply loop through the data, and in order to apply transform, we need to first convert the NumPy array into a pure image, and then we apply the transform to the pure image. Yeah. So the most important things that we need to obtain in a data class that inherit from Lightning data module is to get out the train loader and validation loader. It is optional to have test loader because in training we need train loader and validation loader. So for the train loader here, we simply get the train data by calling the function transform dataset on the train data using the train transformation. And we return the data loader that is applied on this train data with the specified batch size, and we use shuffle to be true because it's just a train loader. For validation, we do the same thing. We will transform the validation data using the transformation for validation, and then we return the data loader. Here in the main function, I write a simple script to load the data and print out some statistics. In order to load the data, we simply call the data module, and here we need to set the state to fit so that we can load the train and the validation data. For the train loader, we simply call data module.train loader, and we can extract the batch image and labels of a batch by using next iter on train loaders. So here we want to print out the shape. I guess we don't need to have this subscript, right? Well, the result for the shape of the batch in the train data will be 128 by 1 by 44 by 44. This is for the batch image. The 128 here stands for the batch size. The one here stands for the one in channel, because we have grayscale image. 44 by 44 here result from applying the cropping to the original image. The original image has shape 48 by 48, but we crop it to an image of size 44 by 44. So here I also want to do the same for the validation loader, and validation loader is a little more it's a little different from the train loader. Well, batch validation, label validations. What happened in the validation data is we apply a transformation that crop the original image into 10 sub-image. So here the transform 10 crops here means that we crop the original image into 10 sub-image, right? And then we merge them. So if we do so, then each of the original image will become 10 sub-image of size 44 by 44. So the batch image here we have shape 128 by 10 by 1 by 44 by 44. So let's print out. Start on a new line. Validation label. There's no need to print out the device. So let's run this and see what is the result. I need to change the directory again. Data.py. It will take some time to load the data from the CSV file. We have this file here. It is quite a big file. But here to recall, we have the train data that is loaded from the CSV file. So each of the image is a grayscale image with shape 48 by 48. After we load the image, we will apply the chain transform, which is a series of random crop, random horizontal flip, and transform to tensors. Okay, so and the same for test. We have the result here. However, for the label, for the validation, it doesn't show the answer as expected. Oh, here I didn't put in the validation shape. Alright, that was careless. And let's continue for the validation data. The transformation that we apply is different. So we transform each of the 48 by 48 image by applying random crop 10 times, right? So each of those images will be cut into 10 sub-image, and then we stack them together. As a result, one image which has original size 1 by 48 by 48 will be transformed into a new image with size 10 by 1 by 44 by 44. Alright, so here we have the answers. So for train image, the shape is as expected, and for validation image, the shape is also as expected. Now we will be talking about the model. So the backbone of the model that I am using to handle this problem is VGG16, and we are going to use Pytorch Lightning for the training. Our model will inherit from the Lightning module, as you can see here. So here I will be implementing VGG16 architecture from the scratch. So in this case, note that we will be using the backbone of VGG16 to extract the core feature of the data, and then on top of that we will attach a linear classifier that maps the features to the number of emotion classes. Here I have a bunch of import, and here there are a few imports that might need explanations. So one of them is weight and bias. I will be using weight and bias to monitor the training process, actually to see all the graph for the training loss and so on. So Torch matrix here is a library that is used to compute the accuracy of the model. And I also draw a confusion matrix which gives us the information about the number of correctly predicted emotions and those that are not correctly predicted. Alright, so here in the init method, we will need to initialize basically the backbone and the classifier in order to set up the model structures. Right? So to make things structures, I will be storing the model informations, the training hyperparameters into separate folders. So in this config folder, I store all the model parameters, the processing and the training parameters. So first let's have a look at the model parameters here. So in the model parameter here, the name is VGG16, and when let's look at the layers here. So in this layer we have a sequence of numbers, different numbers, 64, 128, 256, 512, and we have the letter M. So each integer here is equivalent to a block of convolution 2D with 64 as the input. Let's say from 64 to 64 here, 64 will be the input channel and 64 here will be the output channel. So it is a block. Each of these will indicate a block of convolution 2D, a batch norm, and a ReLU. And the M here stands for max pooling. So let's look at the model structures. Well, so here you can see in the init method, we take in layers, which is a list of integers 64, 128, or 256, or 512. And in between these integers, we have the letter M, which stands for max poolings. We take in the in channel. In our case, in channel is equal to 1 because we take in a grayscale image. Number of class here is the number of emotions, which is 7 in our case. And we also have dropout and learning rate. First, we initialize all these hyperparameters. For the VG16 backbone, we basically write an nn.sequential module that runs through all the integers and the letter M. So for layer in layers, where let me just refer back to the layers here. Layers mean the set of integers or the letter M in between. So whenever we have the layer which is the letter M, we have the NN max pool 2D with kernel and stride both equal to 2. And whenever it is an integers, then we have a block of convolution 2D and batch norm and prelude. For the convolution 2D here, the kernel size is 3 and the padding is 1. So this means when we go through this convolution 2D, the size of the image stay the same, right? And because this is done in an auto-regressive way, every time we go through this, we need to reset the in channel to be the current layer, so that the next time this can be done recursively. And so this whole thing is the VG16 backbone. Once we have gone through all of these, we will add an average pooling in order to extract the features for the top layers, right? So here, well, let me look at this. The top layer here is a max spool with 512 channels. So by applying an average pooling to that 512 channels, we will get a vector of dimension 512. So this average pooling simply collapses all the dimension into one. So now at this point we have a vector of size 512. Yeah, we will make concatenate all the layers into a sequential module, and the top classifier class here is an nn.linear that map from 512 as the input channel to the number of classes that we need to classify. And here in the init method, I also initialize the method in order to compute the accuracy for the training of the model. So in this case, we simply use docmagics.classification.accuracy, where the task is multi-class, and we key in the number of class. And I also have an array, sorry, a list that is used to store validation outputs. And I also initialize the parameters. So note that this way of initializing the parameter is used to force the parameter to start with certain distributions, so it will provide a good starting point for the ways that help the training converge faster. So in this initialization of parameters, we simply initialize all the weights of the nn.linear module, and the weight of the nn.linear module will be initialized to a normal distributions with mean 0.2 and standard deviation 0.02. And furthermore, the bias will be initialized to zeros. So the forward method here is quite straightforward. First, we feed an input, a batch of input image, which has shape 128 by 1 by 44 by 44. We simply feed it through the backbone, right? And doing so will give us an output with shape 128 by 512, 1 by 1. And after that, we will squeeze out the last two dimensions and get the output with shape 128 by 512. And then we will do a dropout on top, which is which give us the output with shape 128 times 512, and then we run through the classifier, and then the final output here is 128 times 7. So for each of the input image, it will give 7 output, which correspond to basically to the 7 logits for the 7 emotions. So these 7 logits are the score for the 7 emotions. The highest logit will give us the prediction for the emotion. In a Pytorch Lightning module, it is most important to implement the forward method, the training step, and the validation step. In the forward method, we simply compute the output given an input tensor x. In the training step, we will need to include training loss and log in any matrix that we want to check. For the validation step, we need to evaluate the model on validation data, and basically in this step we need to log the matrix that we want the model to check, or we want to print out during the training. So let's first look at the forward method. So here the input is a batch of data and it has size 128 times 1 times 44 times 44. First we will feed this input through the backbone, and by doing so we get the output with shape 128 times 512 times 1 times 1. Well, this 1 by 1 here must have come from the fact that we apply an average pooling on top, so all these dimensions that come with 512 will be collapsed into 1, and then we will squeeze out the last 2 dimensions here to get x with shape 128 by 512. We will apply a dropout before we apply the classifier. So the final output has shape 128 by 7. 128 here stand for the 128 input image, and 7 here stand for the 7 emotions. So each image will give us 7 logits, which indicate the score for the 7 emotions. Well, that means the value with the highest score will be the prediction for the emotion. Now is the training step. Training step take in 2 parameters, the batch and the index of the batch. In this training step, we are going to compute the loss, the training loss, and log in any training matrix that we want to print out. So to compute the loss, first we need to compute the prediction and then compare the prediction with the label, right? So x and y here equal to the batch. In this case, x is the input image, y is the labels. Prediction is simply the forward function that we just write apply on x. So the prediction here will give us the logit, and we will compute the loss using the cross entropy functions. So for cross entropy, we need to key the prediction and the target here is y. And here we also log in the chain loss, and we have the option to show it on the progress bar so that we can see the loss go down when we hit train. And on epoch equal to 2 means we will show the loss on epoch. And here we return the loss for the training functions. In the validation step, we need to evaluate the model on the validation data and log in the matrix that we want to check. So this function also take in the batch and the batch index. In this case, note that the data for the validation is different from the data for the training. The reason is because in creating the validation data, we apply the transformation that crop the original image into 10 sub-image. Keep in mind that the original image has shape 48 by 48, and the transformation that we apply crop that original image into 10 sub-image. So the input for this function, the input x here, will have shape 128 by 10 by 1 by 44 by 44. So 10 here is the 10 sub-image. We will need to take average prediction over these 10 sub-image to get the final predictions. First, we will transpose the first 2 dimensions so that the dimension 10 go to the first dimension and 128 go to the second one. The accumulative loss here we start with 0. Predictions, the final prediction here, we initialize it as an array of size 128 by 7. Note that we have 128 image, and each image will give us 7 logits. So the final prediction will have shape 128 by 7. And here there is this device equal to self.device. This will automatically detect the device based on Pytorch Lightning. Pytorch Lightning automatically detect the device that we are using. So now we loop through all the sub-image, 10 sub-image, for I in range basically 10, because the size 0 is 10. for each of the subimage, we give prediction for that subimage and also compute the loss. Right? So prediction is obtained by fitting the subimage to the forward function. The loss is the cross entropy between the prediction and the target. And then we want to average over all the subimage, so we will divide the loss by 10 and also the prediction by 10. Well, for validations, the most important accuracy to check is validation accuracy, right? And this accuracy is computed simply using the Pytorch matrix function that we initialized earlier, and we need to put in the prediction with the target, and we want to show it on the progress bar so we can monitor the training. And here we want to save output for logging in weight and bias. So remember that in the beginning we initialize the validation step output to be an empty list, right? So this list will be used to store the validation outputs, and after each step we will append the output here to the list. And here there is another function called onValidation epoch end. This function is not required in a Pytorch Lightning module. The purpose that I write this function is simply to create a confusion matrix. So at the end of each epoch, we will be doing these functions. So what this function does is simply to create a confusion matrix, plot out all the labels. So on the horizontal axis, we have the predicted, we have the predictions, and on vertical axis we have the real data, and this gives us a matrix that compare between the predictions and the true data. So here it is just a plotting functions. The next important things in a model, a Lightning module, is to configure the optimizers. So in this configures optimizer function, we need to specify the optimizer that we use, and also need to specify any learning rate scheduler. So here I will be using SGD optimizers apply on the parameters with momentum 0.9, weight decay 5e-4. For the learning rate scheduler, I will use reduced learning rate on plateau. The mode here is mean, patient is 5, and factor is 0.1. Well, the return in this function, we need to return the optimizers and the learning rate schedulers. And here note that I want to monitor the learning rate. I need to specify this so that I can monitor the learning rate based on the chain loss. So what happened here is if the chain loss doesn't improve for 5 epochs, we will reduce the learning rate. Right? The interval here is epoch, and frequency here is 1 by default. So here let's just load the model and print out some statistics of the model to make sure that it works. Well, in order to read all these all the config, all these YAML file, I'm using Hydra. Right? So here you see that this way of writing. First, we load the config file by Hydra in this setting at hydra.main. So what this does is it will load the configurations and then pass it into as a parameter of the main functions. So when we do this, the configuration will be passed in as a parameter of the main function. Right? So in this loading, we need to specify the configuration path, the name, and also the versions. And the version here is 1.2. In the main functions, we simply pass in all the parameters that we specify in the YAML file. So here I have 3 YAML files. For model, we have name and we have layers. For processing, we have all the information about the in channel, which is 1. Number of classes is 7, which stands for 7 emotions. I set dropout to 0.5. Learning rate is, the starting learning rate is 3e minus 4, and device is MPS. Batch size is 128, cut size 44. For the training, we will be training for 100 epochs, and we do logging for every 50 steps, which means we do the logging for every 50 batches, and deterministic is set to true. And here for the structure of this, you can see that I create 3 subfolders: model, the parameter for model, for processing, and for training. All of them have the same name, just to simplify the things: default, default, default. And the main file that will be called is config.yaml. And on this file, we simply indicate that on each of the subfolder, we are going to call the default YAML file. And now, with these parameters, let's load the model and print out the number of parameters of the model. So here we will run Python model.py. Well, look like I was not in the directory. Alright, so we have loaded the model successfully, and the model has 14.72 million parameters. Now we come to the exciting part, which is to train the model. So here I have a bunch of import. Hydra for loading the configuration. Logging is for logging the process. And we are going to use Pytorch Lightning. So we import Pytorch Lightning. The Omega config here is also used to write out the configurations that we are using. Basically all these model processing and training parameters. We import the data module and the model, and here we also import some callbacks, and we import weight and bias logger in order to monitor the training. And here we initialize the logger. In the main function here, we first load the configurations, which is this config.yaml file with Hydra. Then by using this setting, the configuration is automatically passed into the main functions as a parameter of the main functions. So here the main function will be doing 2 things. First, it will load the model and the data, and then it will set up the trainer and start training. So first we start by writing out some information about the model and the parameters. And here, to load the model, we simply pass in the layers, the in channel, the number of classes, dropout, and the loading rate. Next, we will be setting the we will be loading the data, right? And here in the load function of the data, we will be setting device to move the data to MPS. And in order to initialize the dataset, we need to put the dataset to the feed mode. So we use dataset.setup with the feed mode. And here we initialize the checkpoint. This could be the place where we store the model. Here the file name will be best checkpoint. We will monitor the model based on the validation accuracy. So after every single epoch, we will save the model that gives us the best validation accuracy. The mod here is max. It's optional to set up an early stopping. Here I already trained for 100 epoch, so I don't use this, but you can try it out. And here we set this up so we can see the information on weight and bias. So note that I use weight and bias for monitoring the training. So in order to do this, it's optional to do this, but maybe it's a good practice. In order to do this, you will need to create a weight and bias account. So you need to go to the website of weight and bias. Let me check it out here. I think I should have given an instructions about this. Alright, so here you will need to go to this website, create an account if you don't have one, and then log in. I already have an account. Well, after you log in, it seems to always give me this default. You will head to project, create a new project, right? With the names here, emotion recognitions, and log in. You need to log in your account. I already logged in here. Let me just open a new terminal. So the command for log in your weight and bias account is weight and bias log in. I'm already currently logged in. If you are not logged in, you will be prompted to authorize the keys for the login, right? So once you are in, you can continue. So now we will be setting up the trainer. If you look at the trainer here, we will need to to pass in the number of epochs. The accelerator, in this case, I use MPS. If you have CUDA, it will make the training be even faster. Locker here I specify to be weight and bias locker. So this is where you need to authorize so that the trainer can be called. Callbacks, here I only use checkpoint callbacks, which is mainly used to store the model with the best validation accuracy. Log every end step, and then deterministics. And after we set up the trainer, we use trainer.fit on the model and the data in order to train. Right? So note that for the data here, when we go data setup fit, it automatically initialize the train and the validation data set. So let me run these models. Well, to make sure I don't interfere with the things that I already trained. Okay, this is the model that I already trained. But let me just give you samples. Why I was just I was out every time I open a new file. So I need to change directory again. It will take a while for the model and the data to be loaded. So here you can see in the beginning here where we code this locker.info, we basically print out all the parameters from the YAML file. So the model name, VG16, all the layers. For the processings, we have all the information about the processings. In fact, this is not even necessary, right, using models here, because we already we already have the model name. We have information about GPU. I use MPS, and here you can see we are starting to initialize the monitoring on weight and bias, and we can view the run at weight and bias. It takes some time to load. Okay, so now we already load the data, and me see what it is now. We load the model, right? We are doing just now we was doing the sanity check. So here you can see that we are already training, and the speed is about 4.8 iteration per second, so it's pretty good. In fact, if you follow me, you will see that I already present about this problem before, but before I don't use the dataset that inherit from the Pytorch Lightning data module, and for that the training speed is not as good as this. It's maybe just a half of this using MPS. I didn't train this on a GPU. I guess if you train on GPU, you may have twice faster speed than this. Here let's just observe for one epoch. So here we can see the chain loss for every step is printed out. And here we are doing the validation. Okay, validation accuracy for the first epoch is 0.38, which is quite good. It will certainly take some time in order to train this for 100 epoch. It's probably take you about if you have GPU, I guess it's about 30 seconds for one epoch. Then it probably take you more than 30 minutes. But here let's observe for one more epoch to make sure our validation accuracy go up or chain loss need to go down. Right now the chain loss is about 1.5. I think it's already going down. Well, the validation is it's taking more time, longer to do the validations, because for each of the image we split it into 10 sub image and do the computation on each of those sub image, right? So the validation will take longer. So here you can see the validation accuracy already go up. Just now we have 0.38 and now we have 0.47, and chain loss go down, so everything is good. I will interrupt the training here because we don't have enough time, right? All right, so the checkpoint will store our best model. So best checkpoint V2 here is the one that was stored just now. And if you want to see the logging of the training using weight and bias, you will need to go here. So I should have all the charts. Well, you can see after about 500 steps, the loss already go down quite significantly, right? And validation accuracies, it's just go up, shoot up straight. So maybe I am overfitting the training. Yeah, I think I might be overfitting the training, the train data. So it might be you might get a better result by applying additional augmentation for the train data. Well, to end this lesson, I want to show you what I get by training for 100 epoch. So that is supposed in lesson 2, but just to give you a peek of what I get. So in order to see what is the performance for the model that I obtained, I just write out a simple Jupyter notebook, and here in this notebook I load the model from the checkpoint that I save, and then we load the configuration in order to initiate the model, right? So here we specify that we load the model from the checkpoint with this with these parameters. And we set up a trainer. Right? A trainer here is simply the Pytorch Lightning trainer. And we set up the data. So we need to initialize the data and set it to fit. We get the validation data loader, and then we validate the model on the validation data loaders. And by running this, I get the following. The validation accuracy is about 70.4%, 0.704, and this is the configuration matrix. Well, I might need to change my on epoch end functions so that this confusion matrix is printed in a prettier manner. So right now it's printed in a scientific form, which doesn't look good. So that is the end for this lessons. I hope you enjoyed. See you next time.